All right, how's everybody doing today?
Pretty good.
Good, good. Okay, Monday. We got 3 weeks until the end of the semester. A couple things we should be able to wrap up. I'm hoping this lesson in the next couple of days. If we're able to go ahead and get started with arithmetic, sequences, and series, fantastic. If not, we will go ahead and do that next week. But what's happening on Friday?
Exam.
Okay, you got your exam over the material we've been looking at, this week, last week, also before the break, what you had your quiz over last week, number set, significant figures, scientific notation. Right now, we're currently on error approximation. But what we're going to go ahead and look at today is continue with the lesson, but we have a focus activity. This one is over Pearson's correlation coefficient. So we actually haven't seen him in quite a while. Let's see here. Steve wanted to see whether there was a relationship between the temperature when he leaves for work in the morning and the time it takes to get to work. He collected data over a 14-day period. So the first part, draw a scatter diagram of the data. All right, so all I really want to do is go ahead and plot these ordered pairs. Okay, starting with, bless you, 25, 35. So that would put me right here. Okay. And this will probably just take about a moment. We'll just run through. Let's go ahead and plot all these. So 19 would give me 42. So let's say maybe right about there. Okay. And then 23, 49. So go all the way up. So 23, 49. Then we have 27, 31. Okay, so maybe right about there. Okay, 32, 37, 35, about right here, maybe. Okay, then 35, 33. Okay, then 30. Whoop, that's a little high. There we go. 29, 31. Okay, we're at the thrilling plotting points portion of the lesson today. So 2747. So let's say right about right here. 2142. So maybe right here. Okay. Then we got 1836. Getting so close. 1645. Right there. 1733. 1738. It's close enough. 28, 48. 48. Maybe we have another 48. Right. Oh, no, 48 would be a little higher. Okay. And our last one, 34, 39. 34, 39 put me right about here. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. Okay, so we got the 2-week period. Okay, so there are my points. Now, does anybody happen to remember, we're going to do this on the technology, and it's been quite a while since we did this by hand. Does anybody happen to remember what the formula is? There were 3 parts to it.
Point slope formula question mark.
No, 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 that is the equation of a line if we wanted to go ahead and start with our trend line or line of best fit. But remember, there were 3 parts to it. R was equal to S sub xy divided by S sub x times S sub y. Do you remember what we called S sub xy? Started with a C. Covariance, yes. Okay. So that was the sum of, it was a product. Do you remember what the 2 quantities were? Oh, so x minus the mean. There we go. Minus x mean times y minus y mean. And then you divide it by the number of terms you have. Remember, that was your covariance, S sub xy. And then what was S sub x and S sub y? That was the standard deviation for your 2 quantities. Okay, so in this case, it's going to represent the standard deviation for the temperature, and S sub y would be the standard deviation of the time. Now, each of these was a radical expression. Does anybody remember what the standard deviation was? Okay, so it's the sum of x minus x's mean squared, and then we divided it by the number of terms. Yes, that was going to be the standard deviation. And then we have the same thing for the y's. So the sum of y minus y mean squared divided by n. Okay. So this is definitely something that you would want to include in your IA if you were going to do a scatter plot. Of course, you would use the technology to go ahead and find it, but you also want to mention the formula and, maybe a little bit about it, okay? Just so the reader, again, would know what it is you're talking about, okay? And speaking of, remember, when's that IA due?
13th.
Okay, next Thursday. Next Thursday, the rough draft is due. So if you need another copy of the rubric or checklist or even the expectations I printed up last week, it's all right over there. If you have any questions, come on and see me. And you don't even have to wait until the 13th. If you feel it's ready and you want to go ahead and turn it in, absolutely, I'll go ahead and take a look at it. All right, but good. How many people would have remembered that off the top of their head? It has been a while. That's okay. That's one of the things that should be provided for you in your formula book. Okay, so we got A taken care of. Let's see. Calculate R to 3 significant figures. Okay, so what we're going to have to do, let me get this data. Now we're just going to go to the calculator because we're not going to bother doing that by hand. We've done that before. Okay, so let's see here. That is a tangent expression. We don't need that. So how would I do this? How do I put in bivariate data? Okay, so list and spreadsheets. Okay, so I'll click 1, list and spreadsheets. Okay. Now we always have to put in a head. Now here you can put in temperature and time. I like to go ahead and just plug in X and Y. Okay. Remember, always avoid this second row here with the equals. That's for if you're doing a spreadsheet, okay, for like a formula. And let's plug in all these values. So 25, 19, 23, 27, 32, 35, whoops, okay. Let's see, 29, 27, 21, 18, 16, 17, 28, and 34. Okay. And what's the shortcut to get back up to the top quickly? Yeah, Control 7. Okay, jumps you right back up. Now the corresponding time, minutes, it says 35 minutes. Then 42, 49, 31, 37, 33, 31, 47, 42, 36, 45, getting close to the end, 33, 48, and finally 39. There we go. All right, so I've got my data in. Now what? Okay, menu. So I'm going to choose just a cell here, go to menu, statistics. I got a text. Stat calculations. Okay. Oh, 2 variable statistics. Now, if we were doing a frequency table, then we'd use 1 variable. We'll actually show the linear regression in just a moment. Okay, so here, the X list is what I titled X. The Y list is what I titled Y. There is no frequency list. Looks like everything's going to show up in column D. Highlight OK. And here we go. So remember, this gives you everything you need. Okay, starting with the mean for the temperature. Which one was my standard deviation? S sub x or sigma sub x? Sigma. Okay, there we go. So 6.053. All right, then we have the same thing for the y values. So we wanted this to how many sig figs? So that would be negative 0.219. Negative 0.219. Yes. There we go. So negative 0.21. Thinking about that 0.19. There we go. And we can throw a 0 in there at the beginning if we want to. All right. And I'm not going to worry about writing it down, but it says describe the relationship between the variables. So this is when we're talking about, positive or negative. Well, obviously it's negative, but is there a strong, moderate, or weak relationship? I'd say there's definitely a weak relationship going on here. Because remember, whether it was positive or negative, the closer it was to 0, the weaker the relationship. And overall, we're not talking about, what was that phrase that we talked about over and over again? Correlation does not mean causation. So even if the value turns out to be extremely high, even 0.99, that doesn't necessarily mean that one influences or causes the other. And this is part of what you can talk about on your IA. It's just another strategy that you can use to help further show that whatever it is you're comparing, is a relationship and this is what you believe it to be, or if there isn't. Hey, Evelyn.
Are we turning in a printed copy of that?
Printed copy, yes. Printed copy, yes.
So, on mine, I measured the table. I didn't realize it told us that temperature would be X and time would be Y. So I just naturally made time X. This is what I've always done.
Oh.
My graph. So my graph is this. So my graph is like correct. I just switched up the variable.
So you just inverted it?
Yeah.
Okay.
Would that really affect my score? Can I just print it in as is?
That'd be fun. Yeah. Did you actually? I'm kind of curious to know.
Like everything I did was the same.
Yeah, everything else should be
So
the
like
same. Even if you invert it, the correlation coefficient should still be the same. Yeah, that's what I'm saying. Okay. All right, and then, is it reasonable to try and find a line of best fit for this data? Okay, no. It is a very weak relationship. In fact, on some of these that we've seen, what's the highest temperature that we go to? Looks like the highest temperature? Looks like that might be 35. Okay, so let's say, for argument's sake, we had didn't have another column on here, but let's say that my R coefficient just happened to show a really strong relationship, like maybe in the 80s. Okay, like 0.8. All right, we went ahead and come up with a line of best fit, okay, to go ahead and a prediction equation to answer questions. Well, let's say I were given something like 40 degrees Celsius. Even though the correlation was pretty high, would I be able to answer with any validity this temperature set at 40? Do you remember what we called that? Extrapolation. There we go. If the value was within the range of what you have, then it was an interpolation. Do you guys remember that? Okay, good. So it's been a while. Now, I know that the regression equation that we could get is going to be worthless, but it's still a good idea to go ahead and make sure that we can get it. So let's say I'm going back over here to my calculator. Okay. Now I'm going to go home. How do we go ahead and get our scatter plot and then get the equation? Okay. There we go. We're going to click this one. Now it just puts the ordered pairs on your screen. So what I always like to do is click Tab. Okay. Always choose the X first. So it lines those up. Tab, then choose the Y. And there we go. So that's the scatter plot that we have on our paper, or looks very, very similar to it. How do I come up with the equation line now? Menu. Analyze. Regression. Show linear, mx plus b. There we go. Like I said, those points are so far apart, I mean, it really wouldn't be worth it to plug anything in. Okay. But good. Does this help? Remember the equation, the process, all that? Okay. All right. How many people are using correlation coefficient in their IA? Good. Okay. Let's go ahead and put that somewhere else. Oops, that is not what I needed. Control W. Do you want to save those changes? No. Okay. Good. Let me go ahead and get rid of that. Yes, we'll save those changes. All right. So put that with the others. I believe I have maybe I have a fifth one. I'm working on it. If we can get it in time. We still have several weeks left. Okay. But at the very least, we now have 4 focus activities, and there should be a few over here if you've misplaced or lost one. But, okay. Let's see. We are not doing inverse trig functions. That is pre-calculus. We were working on this. Okay, so just a few things before we go ahead and get started. Don't forget that your test is on Friday. It's going to cover this material. In fact, this one, the majority of the material is on absolute, relative, and percentage error, but there are a few other topics just kind of thrown in with that. Conversions of time, distances, things of that nature. We also have interval notation. So basically all the material from this lesson and the previous lesson. The significant figures, number sets, scientific notation, that's what your exam is going to be like on Friday. Okay. All right, so let's see. I think we got to the propagation errors. We started talking about absolute error, which is just the difference between the approximated value and the exact value. Like basically how far off you're going to be in units. Okay, the relative error was to take the absolute error and divide by the exact value. So basically, that's the decimal value. When you multiply it by 100, that's the percentage error. It tells you the percentage that you're off as far as your answer is concerned. Okay, then we went through several examples. And I think, yes, we were on these right here, right? Correct? Okay, yes, I got the arrow right there. So I'll tell you what, we can use this one possibly later as a review. I've got another one right here. Let's try this one. Find the errors that result from evaluating A plus B and A times B. And these are just some random error values that I'm going to go ahead and give you. Write the values in 3 sig figs if possible. And I'm not going to worry so much about that because after talking to Mr. Reeves the other day, we're just going to go ahead and round these to the nearest tenth. We're going to keep them consistent with the actual value and the absolute error. And I'm kind of hoping that by now you're starting to see a little bit of the bigger picture. Whatever we're adding or subtracting at the end, that is the absolute error. Okay. So whatever it is we're measuring, whatever I thought the length was compared to what it actually is, that's what we're getting. So hopefully, the other day when we were dividing by these, when I took that absolute error, the 0.1, and I divided it by the 9.7, that's exactly what we're doing when we find absolute, relative, and percentage error. We take the absolute error and we divide it by the relative, or the exact value, I should say. Okay. But let me see what you guys remember about this. I want A plus B. So I'm going to take 9.7, okay, plus or minus 0.1, and I want to add it to 4.2 plus or minus 0.1. Okay, so how do I add and subtract? What do I do here? Adding and subtracting is very, very simple. Okay, Emily, what do you think? Okay, so the actual values, you just go ahead and perform the operation with them. So that would be 13.9.
And then you add the...
Okay, then we add the absolute error. So 0.1 plus 0.1, 0.2. Now, it doesn't say to go ahead and do this, but what if I wanted to subtract the two? Okay, then what is 9.7 minus 4.2? So 5.5 plus or minus, I guess that's going to be 0? There you go. When you add or subtract these propagation error values, you always, always add the absolute errors. So this would again be plus or minus 0.2. Okay. So when it comes to adding and subtracting, it's not too terribly bad. You just have to always, always add the errors. Now, it's when multiplying and dividing that it gets a little different. Okay, let's say I want to take A times B. So 9.7 plus or minus 0.1, and I want to multiply it by 4.2, which is plus or minus 0.1. Okay, so A times B. So how am I going to start this out?
So you first and foremost, you perform the operation on the two values.
Okay, so I'm going to take 9.7 times 4.2. Okay, so let's go over to my calculator. So 9.7 times 4.2. And that's going to give me 40.74. Okay. Now that's already part of my final answer. All right. So I'm going to write the final down here. Okay. So I'm going to go ahead. What was it? 40.7? Okay. I'm just going to go ahead and round it to the same number of places that we had before. Okay. So 40.7 plus or minus. Now this is where it gets a little unusual. What did we do the other day?
Don't you divide the error by...
There you go. You want to take the error and divide by the value that we're given. So I want to take 0.1 and divide it by 9.7. And then I want to take 0.1 and divide it by 4.2. Okay. Now, what we saw the other day, we were going to go ahead and multiply these by 100, but then we were having to go back and divide by 100 because this is going to give me the percentage of the original value, that product that we have to take. So we're not going to worry about multiplying by 100. Okay. So let's see what these are. So 0.1 over 9.7. Okay. There's the first one. And then 0.1. Whoa. That was interesting. And then 0.1 over, what was it, 4.2? Okay. That's going to give me this one right here. So I'm going to take that decimal, plus the other decimal that I just got. Okay. And see, if I had multiplied by 100, well, then we'd be looking for about 3.4%, because the 100 would have given me the decimal over there. But that's the percentage that I want to take of the product that we just got. So that's why we're going to go ahead and not worry about multiplying by 100. All I have to do is take the, I believe it was the 40.74. So this answer times the 40.74. Okay. So 1.39. Now we only have the one decimal place on the error, so I would say 1. Oh, because remember, that was the original value I got when I multiplied 9.7 times 4.2. So these are giving me basically the percentage that I'm going to take of that one right there. So I know that my error should be plus or minus 1.4, whatever the unit of measurement is. Okay. Does that make sense? Okay. I think we were, some people were a little hesitant about that the other day, because it is unusual the first time you see it. Okay. Let's try another one. This one here that we were talking about the other day. You want to try this one on your own? Okay. So let's say x equals, let me go ahead and erase these so you don't have everything running together. So let's say x equals 11.2 plus or minus 0.1, and y equals 3.6 plus or minus 0.1. Okay, let's go ahead and say, find me x minus y, and let's find x divided by y. Now, even though this is division, you still do the same steps we did on the previous problem. But instead of multiplying 11.2 and 3.6, we're going to divide them. You'll perform the operation with those measures however you're giving them. Okay? All right, so let me give you a couple minutes on that. I just want to make sure. We didn't do this one the other day, did we? No. Okay, I didn't think. Okay, make sure. Because you know, math is fun, but we want to keep doing new math, not same math. So 11.2 plus or minus 0.1, 3.6 plus or minus 0.1. Let me go ahead and get this all cleared out.
Oh, yeah. I did 3.2 plus 3.6.
Right, so the subtraction, everybody should be good on right now. Okay, or at least done. We're probably still working on the division, so I'll give you a little more time. But I want to take 11.2 plus or minus 0.1, and I want to subtract 3.6 plus or minus 0.1. Okay, well, I'm going to perform the operation with my given value. So 11.2 minus 3.6. 7.6, would you guys agree? Good. 7.6 plus or minus 0.2. No matter if you're adding or subtracting these values, you always add the errors. So how many people got that one right? Good, good, good. Now the division. How many people are still working on? Okay, let me give you a little more time. Everybody have a good weekend? Yeah. You got a 3-day weekend coming up, too. It was good. It was really good. I mean, I had to stay home all weekend. My daughter, she had a 103 fever on Friday. So it was down by the time I got home on Friday, and it was still about 100 when she woke up Saturday morning, but it finally broke yesterday morning. But we just kept her home just to make sure.
So she left back downstairs.
She's at school. She's at school. So she's still on antibiotics, but she's doing good.
Is it out?
No, I think isn't it the 15th that Amazon Prime members have that, but I don't think it actually comes out to the 21st. Okay. So yes, I will be buying my ticket for the 21st. I won't be able to do the 15th. What new trailers?
Marvel trailers coming out tomorrow, and the fourth Avengers trailers.
Oh, really? They're going to release it? Oh, good. Cool. Oh, we might have to take a gander at it. All right, let me go ahead and catch up to you folks. So what am I going to do first if I want to find x divided by y? Yeah, so I'm going to take the 11.2 and divide by 3.6. Let me go ahead and write this out here. So 11.2, I don't need parentheses now. Plus or minus 0.1 over the 3.6, plus or minus the 0.1. So 11.2 divided by 3.6. Okay. All right, so I'm going to keep one decimal place like we did before. So I know my answer is going to at least start with the 3.1 plus or minus. Now what do I do? Times? Divided, there we go. So 0.1 divided by the 11.2, 0.1 divided by the 3.6, and then whatever values we get from those, we're going to do what? We're going to add those up because that's the percentage I need to take of the 3.1. Okay, now you actually see the percentage if you multiplied it by 100, but we're actually working with a decimal. So controlled divide, we got 0.01 divided by, what was it, 11.6? Or was it 11.2? 11.2, okay. So that's what I got for that one. Control divide, 0.01 over, that's the 3.6, right? Correct? Okay. So there we go. I'm going to add those up. So I'm going to take enter plus. Okay. So this would actually be really small. If I did look at the percentage, it'd only be 0.367%. Okay, so I'm going to multiply this by the original 3.1. Okay, so let me go down here. Where are we? There we go. I'm just going to go ahead and hit times and go back up and highlight that. Oop, went too far. There. Okay. Now, in this case, we'd probably go ahead and make an exception because it was rounded to one decimal place. But if I go ahead and round it to one decimal place, I'm just adding 0. So we'll go ahead and say 0.01. Okay, is this what everybody's getting? Yes, ma'am.
Whenever you were dividing, you did 0.01.
Did I? Oh, dadgummit. Okay, but did you notice that when I did it?
I was confused. I thought I was
Okay. Well, I mean, the exact steps, the process is the same, just with my one mistake. What are you guys getting for your last number then? It is just 0.1? Okay. Sorry about that. All right. Did anybody else happen to notice that while I was typing it? I didn't say anything.
Why didn't you say something?
No. I mean, we've seen me up here more than enough times make a wrong choice, so, it's very, very likely. Okay. But are we feeling better about those problems? Okay, good. All right, let's see here. Moving on. Let's see, error approximation and rounding. So it says use this formula, a equals 2b plus c squared divided by 2d, to evaluate for a if b is equal to 5.25, c is equal to 3.63, and d is equal to 1.35. So it says approximate the value of a to the nearest whole number without using a calculator. Okay. Without using a calculator. All right. So we can go ahead and plug this in. And sure, we can do this, right? Because we don't need a calculator. Sure. Does anybody want to come on up here and show me? Okay. All right. So let's see here. Why don't we go ahead and do this? Because I know we would all be able to do this. Would it be all right if we just plugged it in and then rounded it? Because otherwise it's going to take us some time to get through that. Unless anybody just really wants to do
What
that.
if we rounded it and then did it? Like he rounded like
Well, if we rounded it before, I don't know.
It's like 5. Let's do both. And then
We could do both and just see if it turns out the same. Okay. So let's see here. Help me out with this. This is 2b plus c squared. So make sure I type this in correctly this time. Control divide. So it was 2b, so it's 2 times 5.25, right? Plus c squared. And what was c? 3.63? Whoop. 63. Okay, squared. And then all divided by 2d. And what was d? 1.35. Okay. So here we go. So 8.76922. So that's the exact value. This would be v sub e. Okay. This is the exact one. So I am kind of curious if we were to, now to the nearest number is just going to be 9, right? Okay. So let's see here. If we were to go ahead, like Orion said, and go ahead and round these to the nearest number before we did that, I am kind of curious to see how close we would get. So this would just be 5, this would be 4, and this would be 1. So that would be 10 plus 16 divided by 2. Nope, so that's pretty far off. Okay. 8.7, so like 9. 9 to the nearest whole number. Okay. So if we were to go ahead and round it to the nearest whole number, don't worry about the calculator. Okay, what we believe it to be would be 9. But the exact answer that we got, let's go ahead and say 8.77, just for the fact that we want to put a value on our paper, right? Is everybody okay with that? Okay. So now, what's the relative error associated with this approximation? So we don't look for we're not looking for the percentage. We don't have to multiply it by 100, so we're just finding the decimal value. But in order to find the relative, we have to find the absolute. So remember, the absolute error was the absolute value of what? Was it VA minus VE or the reversal? VA minus VE. Okay, which is equal to the absolute value of 9 minus 8.77. But I'm going to use the approximate value in the calculator. So if we go to this button here, absolute value of 9 minus, click that in, I'm getting 0.231. Okay, equals 0.231. So that would be my absolute error. And we find the relative error by doing what? There you go. For the relative error, we take the absolute, and we go ahead and divide it by v sub e. So I'm going to take this value that we just found, and I'm going to go ahead and divide it by the exact value. So let's do this. Control divide. Okay, let me highlight this one, enter, and then, oop. Hello. Gabby. Okay, there you go. All right, so let me go back up through here. Oops. Come on. There we go. Oh, you know what I'm going to do here? I'll just do this because I think it's going to give me a problem. So I'll just take that previous answer and divide it by, now I'll highlight it. There you go. Okay, so this is what I'm getting for my relative error. Okay. So if I were to go ahead and find the percentage, by what percentage would I be off? Like 2.63, yeah. So I would go ahead and say, since it just wants the relative, I'd probably say 0.026. If you wanted the percentage, but this one was just wanting the relative error. So are we really having any trouble with the absolute, relative error, anything like that? No? Pretty straightforward? Absolutely? Hey, yes. You could. I wouldn't think it's a further math strategy. I mean, you probably could go ahead and incorporate it if you were like you were talking about correlation coefficient. What if you were to go ahead and calculate it by hand or even chi-squared by hand, then calculate it using the technology and see how far you're off percentage-wise? You could absolutely talk about that if you wanted to. Yeah. Okay. I think I had one student last year do that. But that's you could absolutely do that if you want to. Okay. Set builder notation and interval notation. Okay, so this is hopefully going to be something you remember from Algebra 2. If not, that's fine. Okay. But here's what it basically boils down to. This is what we call a solution set. This means all values of x. Do you guys remember that vertical bar? Such that, okay, my values have to be greater than or equal to -3, but less than 5. So when we're talking about equality, if the value is included in the set, we use a bracket, a straight bracket. Okay. If it is not included, then we go ahead and use a parentheses. All right. In fact, it's pretty much the same idea as if you were to take a number line like you did back in Algebra 1 and just go ahead and graph it. Like this here, this solution set is saying the exact same expression here. We're taking all the values between -3 included and 5 not included. So if I were to put this on a number line, I put -3 here, 5 here, and because the -3 is included, remember that would be a closed circle, 5 would be open, and I would shade everything in between. Okay. This interval notation is just another way of writing your range values, basically a set. Okay. How many people are already familiar with interval notation? Good, good, good. And if you're not, that's fine. Okay, let's go ahead and do some examples. The set of all x such that x is less than or equal to -6. Now here's the thing about interval notation. You always have two values. You always go from left to right. You have a smaller and a larger, and they're always going to be separated by a comma. Okay, so here we have an upper value, but I don't have a lower one. So I'm going to put -6 here. So what can I use to represent everything less than -6? Negative infinity, yes. Now the thing about these infinities, we never include them. Woo, there's a table there. We never include infinity because it's an idea. It doesn't represent a specific number. So no matter where the infinity is, positive or negative, it will always have a parentheses on it. Now what about this -6? Is it included or not? Yes, because it does have equality, I'm going to put a bracket on there. So these two items are saying the exact same thing. And if I wanted to go ahead and sketch it, here's my number line. So I'd go ahead, the only value I have is -6. Open or closed? Closed, because it is included. And then I would shade everything less than that. Okay. This is interval notation. Okay. Now this one, the set of all x such that x is less than -4 or greater than or equal to 7. Okay. So what does or mean?
Union.
That's the union. Okay, so sometimes you'll have to create an interval notation where you have two intervals and you'll just connect them using the union. So basically you want to look at each one of these individually. X is less than -4 or x is greater than or equal to 7. Let's go ahead and do the first one together. Okay, so I'm going to go ahead and put my comma. What is -4? Is it a lower or an upper boundary? Okay, it's an upper, so I'm going to put it on the right because it always goes from least to greatest. So -4, and how far lower than -4? Yeah, negative infinity, right? So we never include infinity. What about this -4? It does not have equality, so I'm going to put a parentheses. So that takes care of that one. Now I want to go ahead and do the other one. X greater than or equal to 7. So I'm going to put my comma. Is the 7 the lower or the upper? Okay, the lower, because we want everything bigger than 7. Okay, so how much bigger than 7? Yeah, it doesn't give me a boundary, so I have to go to infinity, which we never include. What about this one? Is it included or no? Because it has equality, it's got that bar, I'm going to go ahead and put the bracket. Now, if you have multiple intervals, you just combine them with a union. So I'm looking for all values in this interval or this one. Okay. In fact, do you guys want to try the next one on your own? Okay. Take a few seconds, see if you can figure out what that is. And I'll go ahead and give you another one. The set of all x such that x is greater than 9. Okay. All right. So I'm going to go ahead and put my comma. Somebody help me out. Should I start with a parentheses or a bracket? Okay, parentheses. What? 9, comma, infinity, and we never include it. Now, why wouldn't we put a bracket here? There you go. It just says greater than. It doesn't specifically say greater than or equal to. Yes. There you go. Now, one very common phrase that comes up a lot is all reals. How would you write all reals in interval notation?
Negative infinity.
Okay. All reals. Negative to positive infinity. Yes. Okay. Good, good, good. You want me to go ahead and give you a few others, or do you guys feel okay with that? Think we're okay? All right. Well, let's see what we got next. Standard units of measurement. Now, a lot of these you're going to know just off the top of your head. It's the other ones, but if I ever give you like a quiz or a test or something where you need these, I'm not going to have you commit them to memory because you should be provided a lot of these anyway in your formula booklet. But the International System of Units, SI, is a set of standard units of measurement that are used worldwide. Many of the U.S. measurement units differ from these standard units, so it is important to be able to convert from one unit to another accurately. We always like to do things different here. We need to go metric. But anyways, time. The base unit of time in SI is the second. Unlike most units within the SI system, conversions of time are not based upon powers of 10. They are based on the external influence of the sun, the moon, and Earth's rotation. And, you know, we're familiar with all of these. 1 minute, 60 seconds. 1 day is 24 hours. Now, 1 year is 12 months. But 360, now typically people go ahead and say 365 days, and they usually forget about that 1 quarter day, because what happens every 4 years? You have a leap year. And what month has the extra day? February, yes, there you go. 1 hour is 60 minutes, which is 3,600 seconds. 1 week is 7 days. And then we start getting a lot smaller. This is when we use base 10. For time less than 1 second, base 10 is used. Small units of time are becoming more common with the advances in computer technology. 1 microsecond equals 1 millionth of a second. 1 nanosecond equals 1 billionth of a second. Okay, so just a fraction of time. Now, for time greater than 1 year, base 10 is also used. So a decade is 10, century 100, millennium is 1,000. Okay. And now we're to time zones. Oh, and I got 207. So let's go ahead and stop there. It's about time. It's about time. Yes, there you go. All right. All right.